All right, good afternoon.
Good afternoon.
Well, we are back for week 6 out of 10. So we're getting through the good stuff now. And we are past the halfway point. So my main plans for today are to answer any questions about the midterm. So midterms are graded, and I posted grades and some comments. But we can talk about any questions about the midterm first. And then I want to go ahead and talk a little more about PA3, answer any questions you have on PA3, but also make some general comments about that. And then just go back to continuing to keep digging into trees and how to deal with tree-like structures. So let's start with the midterm. If there's any questions or anything you want to go over on that, let's start with that. And I see a microphone that's unmuted, but I'm not hearing anything.
I felt pretty solid on it.
That's good.
You go through 1D for me.
Yeah.
Just want to get a better idea of what we were looking at. I kind of came back to that one and tried something, but
So
interested.
and this might be the double asterisk thing that some people got tripped up on. So 1D, so what's our setup here? We've got a data structure named access. It's got these fields. And so we're trying to declare an array of objects of this type, this struct access. And so I always try to go back to simpler cases when I'm trying to figure out how to do something. So for example, if I have an integer, I can say integer I. If I want an array of integers, I can say integer star data. Or if I know up front that I want, say, an array of 10 integers, I could say integer data bracket 10. Right? So this is just a plain old single variable, but for an array I have two ways to declare an array. Either like that, if I happen to know the exact size, or like this, which makes data exactly the same type of thing as it is here. But if I do this, it not only says data is, a pointer to an int, but it allocates memory for 10 integers, and it initializes data to point to that first location that was allocated. So this does that plus two other things. So in questions D and E, you were doing this part in part D, and then in part E, you were doing the allocation and assignment of the memory to actually hold 25 of these elements. But in D, we're told we want to declare an array of unknown length. So the type of thing is going to be a struct access. So we're going to want to say struct access star. And the array should be named all records. So it's struct access star all records.
Okay, that makes more sense.
Okay. And like I say, for me, I don't do well memorizing like esoteric rules. So I try to like go back to, something less confusing and then build it up from there. And then for completeness, in part E we want to allocate space sufficient for an array of 25 struct accesses. So we're going to use malloc. We're going to need the size of one struct access, and we need 25 times that size. And so that would allocate the space and then set all records equal to that. And after we do that, we could, in our code, say something like all records bracket 0 or bracket 5 or, you know, bracket 24, or more generally bracket some expression, and it'll do the right thing. So question 2, by and large, looked like people had a pretty good handle on this. This is, you know, trying to manipulate structures with a few lines of C instead of writing a delete function and saying delete 400. We're shown exactly what the list is, and we're given a pointer to this first node and asked to do the kinds of things that would cause this 400 node to be deleted. And I saw a lot of cases where people made really good use of temporary variables. And this was something that I've suggested can be useful. And people definitely took advantage of this. So let me show you a picture of this. And so so the print statements, you just have to follow these things out. So list arrow data should be pretty straightforward because this is list. List is pointing to a struct node. And so list arrow data says, you know, take the thing that it points to, which is this node, and look at the data field. Well, the data field is 0. So this part is going to be equivalent to a 0. So the data equals %d, that's going to print out a 0. List arrow next arrow data, you have to do a little bit more work. You have to say, well, this is list. List arrow next is whatever's in this lower part of the node, the next field, right? And so if you take that thing, which is pointing to the -1 node, and you say that thing arrow data, it means go to what it points to, which is this -1 node, and look at the data field. Well, that's -1. And so this should print out, you know, data equals -1 space data equals 0. So that's what should be printed by it. And a number of people just said -1 0 or said -1 comma 0, and I didn't take off for that. But, you know, technically what would be printed by this is data equals -1 space data equals 0, right? And if you happen to have a teacher that was super picky, you might lose points if you just say -1 0. But I assume people know how to use a printf statement, so I wasn't really checking for that. But so that's technically what it would print. And then trying to delete the 400 node. So, you know, you can get into all kinds of list arrow next equals list arrow next arrow next arrow next, and do you want 2 of these or do you want 3 of these, and all this business, right? But you can always make use of temporary variables. Now I said you're not allowed to use any loops, but you can write as much code as you want. And so here's a way to tackle this kind of problem. I could say first equals list arrow next. Well, if list is pointing to my sentinel node, first is the thing that this points to. That's this node right here. And I could say second, I want it to be this node right here. Well, that's just what first is pointing to. So here's second. And then third, I can set to whatever second points to. And you've got to declare these. You've got to say struct node star, right? So this has got to be valid C. But as a way to approach this, right, I can first make temporary variables that point to these 3 things. And now, you know, I want to delete this node called second. Well, to take it out of the list, I simply want first to point to third. So I can say first arrow next equals third. And then I have to free the memory of the node that's no longer part of the list. I can just free second. And that's much safer. It's much less likely to have an error than trying to do it all with just, relative to list. But, this is telling me that, well, what's first? It's list next. So list next should be equal to list next, right? But if that doesn't ring, right with meaning to you, break it down into pieces like this. And it's something we're going to almost need to do when we get deeper into trees, because the levels of indirection we're going to do are going to be a few levels deep. But this is a nice, safe way to do that. And I saw a number of people do this, which is great, especially on a test, because it minimizes the chance of a careless mistake. And then creating a new node with a value of 87. So, after you've done this, struct node star new equals malloc, and remember it's size of struct node. And I'm guessing, yeah, this is a struct node, right? So malloc size of struct node, and store that into the struct node new. So now I've got a new node with an 87 in it. If I say new arrow data equals 87. So that's what you get for part C. And then for D, write some C code to insert that node immediately after the -1. So I want to squeeze it in right here. And so how do you insert a node? Well, new next equals, and assuming I've already named this node first, it should have my new node point to whatever my first node is pointing to. And then my first node points to my new node. So that sets this up to point here, and it sets this to point there. And the specific example here is not terribly interesting or relevant, but it's the process of being able to do this. If you can do this, then figuring out how you want to manipulate data structures in the future, like with binary trees, will be a lot easier. And if this doesn't make pretty good sense, right, then try to do some of this in code. Write some code for this, compile it with a -G, go inside GDB, and step through your code. And after each step, take a look at memory, see what things have been set up, and maybe build this list by hand and then go through some of these operations and make peace with that. Alright, and then question 3, you've got a linked list for storing integers. There's an extra field in each node called initial. It's a character. And your goal is to make a function named product that multiplies all of the data fields for any node where initial matches something that you've been given as an argument to the product function. So you're given a character in addition to the sentinel node of the linked list. And you want to multiply the data field in all the nodes where the initial value matches the value of the trigger, and then return that product. And I got the sense that some people didn't understand what they were being asked to do, but I think only one person asked me any questions about this question on the test. If you don't know what it's supposed to do, definitely ask. Right? Worst case, I'll say you have to figure that out. But, you know, if you're not sure, am I supposed to multiply all the values or just the first value? Am I supposed to change the list? You know, whatever. You can always ask during the test. And I'll either give you some clarification or, you know, maybe I'll say, well, that's part of the question is figuring that out. But if it's a question of understanding what you're being asked to do, definitely at least take a shot at asking for clarification. So this is a product function. It takes a sentinel node, as most of our things do, and it takes a single character, which we called trigger. And we're calculating a product of a number of nodes. And we know with a linked list, right, we can't just, you know, look at all the nodes at once. Anytime we deal with a linked list, it's the same drill. Start with the sentinel, move from node to node, following the links until you get to the end of the list. So we're only going to encounter these values, you know, one at a time. And we're thinking of a list like this. So here's our sentinel. And here's a 5 and an X, and here's a 3 and a Y, and here's a 6 and an X, and here's a 7 and an A, and here's a 2 and a B, and there's the end of the list. And so if I say product sentinel X, I should go through in every node where the initial is equal to X, I want to multiply those data values together. So this would be 5 times 6, this would return 30. If I said product of sentinel, comma B, it would find every node where the initial was equal to B and multiply those. Well, there's only one node, which is a 2, this would return a 2. If I did product of sentinel Q, it would look for every node where the initial matches Q. It doesn't find any, and it says if there are no nodes with initial equal to trigger, return a product of 1. So it's multiplying all the nodes in your list, but with the one wrinkle that it's ignoring any nodes where this initial is not equal to whatever trigger you passed. So you're subsetting the list. Well, you got to do some kind of running product, right? It's like a running sum, but you're multiplying instead of adding. To do a running product, you need to initialize. And for a product, we initialize to 1 because we're multiplying. For a running sum, we initialize to 0 because we're adding. So we'll initialize result to 1. And now you need to prepare to march down the list. Now you can use the sentinel as a local, but it's pretty common to make a new temporary variable. So I'm going to make a temporary variable. I'm going to initialize it to sentinel arrow next. So here's the first value of my temporary variable. And my mindset is temp points to the node we're looking at right now. So what's the desert island algorithm? If you're doing this, you know, with pencil and paper instead of a computer, how do you do this? You know what the trigger is, okay? The trigger is X, so you remember that. Look at your node. If the initial is equal to X, multiply your product by a 5. Regardless of whether you use this node or not, go to the next node. Look at the initial. It's a Y. It does not match the trigger. I'm not going to multiply by a 3. Go to the next node. The initial is an X. That matches my trigger. Multiply your product by 6. Go to the next node. Initial is an A. Don't multiply. Go to the next node. Initial is a B. Don't multiply. try to go to the next node is null, we're done, return the product. So we can put that into code. So this is our usual way of moving down a linked list. Right, while temp is not null. But this, you might choose to do this a different way. It's personal taste. Some people prefer to initialize temp to the sentinel node and then say, well, temp next is not null. And some people prefer to move to the next node at the beginning of a loop or to move to the next node at the bottom of the loop. There are a lot of different ways to do it. What you want to find is a way that you know how to do it that makes sense to you, that you can keep straight, that you can feel confident about what's going on inside the loop. So it's not going to be just the way that I write it down, unless that happens to be a way that resonates with you. But how do you find this? You've done this in PA1, you've done it in PA2, you're doing it in PA3, right? So the more you work with it, the more test code you write, the more you go into the debugger and see what's happening, right? You'll start to conceptualize at deeper and deeper levels what's going on in a loop like this. I can write the code here, and I'm going to write the code here, but that by itself is not really worth a whole lot. What's worth a lot is seeing this process in a way that makes sense to you, in a way that you can work with and that you can come up with in the future. So here's one way to do this. Well, temp is not equal to null, and temp is the node we're looking at. So if temp initial equals trigger, and remember, characters are like integers. So you can copy them with an equal sign, you can compare them with a double equal sign. They're different from strings. A string is a collection of characters, it's an array. You can't compare strings with double equal signs, you have to use string compare. You can't copy strings with one equal sign, you have to use string copy. But for characters, you can just do a plain old double equal sign. So if temp initial equals trigger, then result equals result times temp data. So multiply your running product by this node's data. And then our usual, move down the list. And iterate until you've hit the end of the list, and then at that point just return your answer. So something like that. So some of the troubles I saw people running into, one issue was doing this multiplication without looking to see if the initial matches the trigger. In other words, multiplying every node in the linked list, which misses this whole idea of multiplying multiply the values of the data field in all nodes where the initial value matches the value of the trigger. I misspelled trigger, end value. So that was one thing I saw, was people multiplying every single node instead of doing it selectively. A lot of people returned after multiplying one number instead of multiplying all the numbers in the list where the initial matches the trigger. As soon as they did a multiplication, they returned. And I'm actually seeing this in some programming assignments, and I'm seeing this on Discord somewhat. Remember, as soon as you say return, your function is done. Right? This is not saying when the function exits, return the value of result. This is saying exit the function right here, right now. And so if I put a return statement right here, I'm going to return the first time through the loop. And it's never going to do anything else after that. Right? So return means exit the function. So that was an issue in a few cases. A lot of people changed the list. And if you change the Sentinel node, that was okay. But if you actually change the list itself, this is a destructive procedure. And there's nothing about the description that says this function should, you know, erase the list from memory, or change the list, or remove nodes from the list, or things like that. The list is an input. It's a place you're getting information from, but when you're done calculating the product, this list should look exactly like it did before your product was called. Right? It would be like, you know, calling the print function, and after you finish printing the value of I has changed value. Well, it wouldn't be a very good print function in that case, right? So watch out for those side effects. What else? The usual challenges with going through a linked list. Like I say, there's different ways you can do this. If you do while temp arrow next is not null, you will miss the last node of your list. Because if temp is pointing right here, temp arrow next will be null, but I still have this node I have to process. So unless I'm processing things one ahead in my list, I want to check for temp is not equal to null. Or if I do temp equals temp arrow next inside here, I might potentially segfault, because temp arrow next could be null, and then when I try to look at its initial, I might get a segfault. In fact, I'm guaranteed to segfault eventually. So the usual business that we've been working on in PA1, PA2, of knowing how to go through a list and make sure you start in the right way so that you pick up the first node, you don't pick up the Sentinel node, you pick up the last node, and you don't try to pick up something after the last node. So you've really got to kind of dial it in on both the beginning and the end of the list. I think those are the main complications I saw people run into. All right, short answers. Abstract definition of a queue. So a queue comes with a remove method, an add method, an init method, possibly, you know, is empty, is full, that kind of stuff. But this has nothing to do with the abstract definition of a queue. When we talk about what it means to be a queue, we never talk about, you know, a next field or a data field or an arrow. These are implementation details. These have to do with how we might choose to write code to implement a queue. Just like when you choose to implement an automobile, you might use, you know, such and such type rubber gaskets and you know, 8 cylinders and so on and so forth. But that's not part of the abstract definition of a car, right? Perhaps. A car is a thing you sit in and you can start it and you can move and stop and turn. I know cars are more than that. So this is the one that does not belong, right? This is not part of an abstract queue. This looks like part of an implementation of a queue using a linked list, probably. Which data structure would be most likely used for schedule processing in an operating system? That would be a queue. If you said heap, I gave you credit for that. I don't think anybody did. But a queue, right? Usually we schedule jobs first come, first serve. That's a queue. That's another way of saying FIFO. If we scheduled the last job that was requested first, then, you know, a job that started yesterday might never finish, because every time somebody put a new job in, that old job would be told to wait, and you take care of the new job. So definitely not a stack, but a queue usually works well. And operating system process scheduling is one of the examples we used. Which of the following is equivalent to pointer arrow field? Let's take the pointer, dereference it with a star, and then access the field of it. And I tried to comment in people's codes, if you're doing this in your code, don't, right? It becomes a habit. Try to break that habit right now. If you want to do this instead. Because this will get you into all kinds of issues when we start doing more complex things like list arrow, next arrow, next arrow data. And we're going to keep going in that direction throughout the term. And if you ever do this, you know, in a course other than mine, it's going to definitely raise eyebrows. And I can't predict how a teacher would react to that. If they would give you like an automatic 0 or what, I don't know. But this is the way to dereference a pointer and access a field. So try to stick with that. Alright, so that's equivalent to C. Which of the following is the main advantage of using a makefile? Makefiles do not help you identify memory leaks, other than they let you compile your program quickly so you can run Valgrind more quickly. It does not help you check syntax, other than, you know, GCC will give you syntax errors, and a makefile, you know, runs GCC usually. Compiling a program with make will always take less CPU time than using GCC. That is not true. It has no effect on how long GCC takes to do its thing. But it does let you compile files that only the files that need recompiling. And so this is what we've meant by a good makefile, starting with program 1. When I said you need to have a good, high-quality makefile, what we mean by that is, you know, a file that compiles only the things that need to be compiled. So GCC star.c is the extreme opposite of that. That says compile anything you find in this directory that ends with a .c. And if I change one file and I say GCC star.c, all 20 files in my directory get recompiled. A makefile is the opposite of that. It lets me say, hey, you know, if you changed blah.c, you only have to recompile blah.c. But if you change functions.c, you also have to compile, besides functions.c, these 2 other C files also, and so on. So the answer there is D. Structure known as a LIFO, that's a stack, last in, first out. That you either knew, or it was on your sheet, or you didn't, but we've used LIFO a few times in class. Collision handling strategy where you rehash following a collision, that's probing. So that's the alternative to chaining. PA3, we're doing chaining. We have a linked list at each entry in the hash table. Probing, you hash a key, you try to put it in the table, there's something there, you hash it again with a different hash function. Usually a hash function with a different argument. So that's what probing is. Alright, generally true about hashes. Hashes improve the efficiency of storing a key data pair versus parallel arrays. That's one of the main advantages of a hash. If you just have parallel arrays, you need to either, you know, put them in the middle and move things down, or do something, right? And a hash makes that efficient because the hash function tells you exactly where to store this thing in an array. Hashes take less space? Probably not. They probably take more space, actually, because you have some overhead to keep track of. Hashes can only handle keys that are null-terminated strings? Absolutely not. So we've been using strings mostly for our keys, but as I've said, they could be, you know, integers, they could be binary strings, they could be the contents of JPEG files or music files, and so on. Hashes improve the efficiency of deleting a key data pair. That's absolutely true. Because again, the hash function tells us exactly where to find the key in our array, and then to delete it, we basically, you know, usually clear a flag or delete it from a linked list. Alright, and then for overall efficiency of a hash table, what's the most important characteristic of the hash function? And this has to do with collisions, right? It should not take many steps. Well, when you see many in an answer, you should be suspicious because that's so subjective. But you know, a hash function might take 100 steps. It might take 1,000 steps. It might take 1,000,000 steps. But the key to the speed of a hash function, a hash table, is not how quickly we can calculate the hash value of a key. The thing that makes a hash table so efficient is that once we've calculated the hash value, hopefully we can just store our data right there, or retrieve our data from right there, or delete our data from right there. And we don't have to do any hunting around, because the hunting around is the thing that gets worse the more data you have. and that's our main measure of complexity, time complexity, is, you know, as you get more data, what happens to the time? So the amount of time it takes to calculate a hash value is not really the critical piece. Not involving any loops, it's pretty hard to imagine a reasonable hash function that doesn't involve loops. And not using much memory, well, you know, again, we've got memory on the system. You call a hash function, it returns whatever memory it uses is presumably free after the function returns. So that's not really an issue, and it's definitely not an issue for overall efficiency. But this one is key, right? The expected set of keys should get hashed to different locations. In other words, we should have minimized collisions. So a good hash function will take different keys to different locations, and we get that nice order 1 behavior. A poor hash function might take all of our keys and map them to only one of 5 locations, and now we're getting tons of collisions. And that kills the efficiency, taking you down potentially to order n. All right, so any other questions on that? All right, so let's talk about grades. So some people did really well on this exam. There were some hundreds. There were some 90s. A number of people probably did lower than they wanted to. And I think the most important reaction to that situation is to try to figure out how to course correct. Now, you know, whatever you got on the midterm, it does not, you know, take you out of contention to pass the course. Okay? But if you scored, you know, lower on the midterm than you wanted to, let's use this as an opportunity to say, hey, you know, I thought I understood such and such, but apparently I didn't. Well, if that's something that's going on, we can talk about that. We can talk about how to self-assess your understanding of something. And part of that comes out, you know, from working on the programming assignments. And if you're programming by trial and error, or if you're finding pieces of code and putting them together and changing things until it works and so on, then that's can be a clue to, you know, you might think you understand linked lists, but maybe you don't, right? And so we can talk about, you know, how to sort of assess one's understanding, and then how to rectify that if it turns out, you know, I really don't understand anything about stacks, or I don't get hash tables, you know, or linked lists. We can talk about how to get some practice with that and you know, get back up to speed on it. It may be that you know, there's a test anxiety issue, or a general issue with working in a time limit where you know, you tend to lose track of time, and the first problem you start working on, you know, you look up and 30 minutes have passed, right? And there are strategies that can be, you know, used to help mitigate that. And there's also accommodations that can be made. There's ways to arrange to have extended testing time and so on and so forth. It may be that the word test, you know, makes your brain lock up. And, you know, this happens to some very good students who understand material, who do well on assignments, but they get to the test, and as soon as they think the word test, they kind of freeze. And they might spend, you know, half of the test period just staring at the test and reading each question and flipping from page to page, and they're kind of in a brain lock, right? And so that's like a test anxiety thing. And there's techniques for dealing with that, and there's accommodations that can be made for that, and so on and so forth. So if you feel like you got a lower grade on the midterm than you wanted, let's definitely talk. And let's A, try to figure out what's going on, and B, try to figure out what can be done to change that going forward and going into the final. And these things will help not just with this course, but potentially with every course you take. And so this is an opportunity to sort of like dig into that. And so send me a note or come by office hours and let's get a dialogue going on that. And as I said, the grade is not sink or swim. It's factored in with everything else in the course. But also it's a midterm, right? The final is in many ways much more important because it's cumulative. So I don't have any predefined extra credit opportunities. But whatever you might do, whatever you might spend time and energy wise for extra credit, I would say you can spend that probably better, figuring out how to get more comfortable with the concepts, writing more test code, going back over things that you might have not done perfectly and digging into those, practicing, debugging code with GDB, looking at linked lists from different perspectives, things like that. There's definitely things you can do that don't necessarily get you extra credit, but will help with getting you more points on future assignments and exams. And I think that's a good way to use your time and energy. So someone's saying in chat, PA3, malloking strings and freeing things and so on. And let me make a general comment here. So I want to spend some time going through some pieces of PA3, including looking more detailed at strings and when to malloc and free and all that kind of stuff. But I've been noticing on Discord a lot of conversation about this business of mallocing a string and copying something into a string and freeing a string. And there's been some really interesting, deep conversations in Discord, but they are going very, very much deeper than you need to for PA3. And so I've had people who are coming to PA3 and they're trying to figure out, how do I copy the first name into this variable, and they're finding deep conversations on Discord that are talking about different types of memory on the heap versus the stack versus something else, and different aspects of programming languages and operating system design and all this kind of stuff. And that's way deeper than it has to be for PA3. So we're gonna put together some code and dig into some of these aspects. But if you feel like you're getting lost on Discord, maybe it's not the best conversation chain to try to use right now to learn this stuff. If you're confused about how to set up space for strings or how to copy things into strings, let me know. And it's probably a lot easier than some of the conversations are making it out to be. And some of those conversations are looping in former students who are at a university or have finished university. And so there's good information there. It's just information that may be more than we need at this point. And so if you know that this is, extra stuff that's interesting and so on, that's great. But if you get caught up thinking that you have to figure out all of this stuff to make PA3 work, you're probably making things too hard on yourself.
Quick question regarding PA3.
Okay.
So, I have mine set up to where it opens the file, and if you put the wrong file name, it'll kick it out and say invalid file.
Okay.
I don't know if you're checking for that, but I'd just like to be complete on it.
Mm-hmm.
But if you put in just temp, the directory, and you hit enter, it runs on yours, it also runs on mine, but it doesn't add anything, obviously, because it's not a file.
Yeah.
But it still allows the program to run. Is there a way to check that, or do I need to worry about that at all?
Um, I'm slightly surprised it runs on mine, but I'm not totally surprised. Um, the main thing to check for is you don't want a seg fault. And so if you open a file and it doesn't exist or you don't have access to it and you don't notice that and you start trying to do your fgets, you'll seg fault. So you're right to check that and kick out of the program if you can't open the file. But really, the way that this assignment is written, just about anything is a valid database file. And it will happily, you know, suck in whatever information you give it and treat it like a database of plates and names. And that's okay. I'm not going to, you know, take off points for that, particularly if my code's doing the same thing. You know, if you wanted to check that, there's a few things you could do. You could, you know, analyze each input line more carefully and make sure it consists of exactly 3 strings with spaces in between. And that would be one way. A typical way this is handled in practice is you would require something in the beginning of the file, like a particular combination of binary characters, or something to indicate this is a license plate database file. And the first thing you might do is, you know, read the first line and look for that tag. And so if you know, if you have a main program and you look at it, you always see this control question mark elf in the first 4 characters. And that's in there to indicate this is an executable file that's runnable on this system. And if this is not in here, then when you try to run this, it'll say there's a format error. And so you could do something like that. You can also check the status of the file from your C program and see if it's at least a plain file as opposed to a directory. And that can get you a little further. But as far as the format, you know, unless you're checking the syntax of each line, the code's probably just going to ingest whatever's in there and just treat it as, you know, a plate, first name and last name.
Okay.
Wonder if I can fix this file. Usually when you edit a file with a text editor, it does more than just what you added. Let me see. Hey, it actually worked. Cool. That's Unix. All right. Other questions?
For the print, when you use the hash find function, and you print the first and last name, do you want that in the main program or in the actual function?
Hold on, let me pull up the assignment so I don't like make stuff up.
Yeah, it says return first and or it says load first and last name into first name and last name. So I assume that means return it, but I just want to be sure.
So which function are we looking at? Print? There's no print.
No, it's going to be the hash find.
Hash find. So hash find does 2 things, right? It searches for the plate in the hash table, and it does 2 things. If it's not found, it just returns a 0. But if it is found, it returns a 1, but it also takes the matching first name and last name and loads them into these arguments.
Okay, and then the main program will interpret that and the first and last name. Okay. I had one about the hash size global. So you told us not to declare it in main, but would it be okay if we put it in the header so that we can still access it in main?
You should not need to access it in main.
Okay.
Your main program should call hash init and specify a size, which you get from the command line. But when you say hash add, hash find, hash load, hash dump, hash free, none of these require the hash table size to be sent.
I was using it for the dump command, but yeah, I could probably just make another variable for it.
Yeah, so hash dump, you pass it the hash table and the number of the cell you want to dump.
Oh, no, I meant about the command line program needing to know what the hash size is.
Oh, yeah.
I can still just make a variable for it when I, you know, init the list.
Yeah, I'm curious about something though. Because I think what I might do is make a hash dump all function. Because sometimes you need to dump the entire table, right?
Yeah.
So you could make a hash dump all as part of your hash package, and that has access to the hash table size, and so that could call hash dump for each cell.
Right.
That might be a nice clean way to do it.
Yeah. I'm
curious what I did though.
Yeah, I just made a separate variable and said if the num is equal to that variable, then just dump the whole table. Otherwise,
right.
Dump just that index.
Oh no, main already knows what the hash table size is. Right.
Yeah, I could. I felt like being sly about it with that.
Yeah, no, I mean it knows it because it's told that value when you run the program. It gets it from the arguments or it sets it to 100.
Yeah.
So just keep that in a local variable in main, and then you can use that in a for loop to call hash dump.
Yeah. That was how I was gonna do it.
Okay.
Like, don't put it in the header. But
Yeah, that seems good. All right. Anything else before we? I'm going to go through some details of PA2, but PA3. But any other questions from you first? Okay. Well, let's do a 5-minute break before we switch gears, and let's come back. Where am I? Hold on. All right, let's come back at 2 o'clock, and we'll go through some more detailed code examples for some of these things about passing arguments back and forth, and dealing with the static table size and so on. So I'll meet you back here in about 5 minutes. So let's look at passing strings. And let's start off with some code. So, first thing is, if you want to declare a string, you've got a couple of options. I can do this, and this is saying that, you know, hey compiler, when I say name, N-A-M-E, talking about the address of a character. And that's, to the compiler, that's the same thing as if I said this. This says, hey compiler, when I say name, I'm talking about the address of a character. But the difference is, this statement is not only telling the compiler that, but it's also saying, hey, and by the way, find me 100 characters in memory that are free. Find me a chunk of 100 memory locations that I can use. And now set name equal to the address of the first character. So if I say car name bracket 100, and this does three things. One, name is the address of a character. Two, somewhere in memory, it finds a block. In this case, 100 bytes long. And three, it says name should be set to the address of that first byte. So all three of these things happen when you say car name bracket 100. Now if I just say car star name, that does the same thing as this first thing up here. It says name is the address of a character. But it has not been given a value. It's like integer I says I is an integer, but we have no idea what the value of I is. All we know is it's an integer. Well, car star name says name is the address of a character, but we don't know what that address is. And so before we could do anything with name, we have to say malloc 100 times size of a character. And that, you know, creates a block of memory 100 bytes long somewhere. So that takes care of this piece. But this still has nothing to do with name unless we also do something like name equals malloc. And now name is whatever this function returns. Well, this function returns the address of the first byte in this block. And so this statement sets name equal to that address, so that takes care of this thing. So I can say car name bracket 100. Sorry, I didn't know I had terrible glare on there. I can say car name bracket 100, or I can do car star name and then do a malloc. And in the end, the effect is basically the same. I think as soon as I close the shades, the squirrels are going to like attack the bird feeder, because we're having a little battle right now. That's okay. All right, so that's the first thing, right? Declaring these variables. if you know that you want a character that's going to hold, 100, string that's going to hold 100 characters, you can usually just do this. But if you know that you're going to have a string, but you don't know how long it is, there's a good chance you want to do this. All right, so let's look at some of our functions from this perspective. So let's see. All right, so let's just think about the list functions. And I keep telling people, if you're not sure about this, start with a list. Forget about the hash. If you clearly understand how the list functions work to a level that allows you to code them, the hash functions become easy. All the stuff you need to figure out, most of the stuff you need to figure out, you'll figure out by doing a list functions. And the list as a structure, a linked list, you understand pretty well at this point. So this is a really good place to focus your initial efforts. And let's just look at the listAdd function. So the function itself, listAdd, well, let's look at listFind. We'll go back and look at listAdd in a minute, but let's look at listFind, which is what we call to search the linked list. So we pass a sentinel node, a plate, a first, and a last. All right, so look at the description of this, right? Search for the given plate in the linked list. That's this. So we're passing in a plate. It's going to be a pointer to a memory location that contains a string, a set of characters followed by a null terminator. So search for the given plate in the linked list. If found, load the matching first and last name into these variables, first name and last name, and return a 1. If it's not found, it's easy. Just return a 0. Didn't find it. But if you find a node in your list with this matching plate, what we want to do is read the first and last names from the node and copy them into these variables. All right, so let's dig into that. Here's the listFind function. Suppose that I was just testing this. You're developing your list. You're going to write your own main program. And so here's my main. So I'm going to do, and there's some pseudocode in here. I'm going to do, list equals list init. And I'm going to do listAdd list p1 first name last name. You can be more creative than that if you want. But, if I've written my functions and I think they work, I can call list init. That should return a struct node star. So, make this list a struct node star. And then I can call the listAdd function, and listAdd takes a sentinel node. That's the thing we got back from list init. A plate, a first name, and a last name. And these plate, first name, and last name variables are strings. So this is saying, hey, add to my list this license plate P1 with a first name of F1 and a last name of L1. And now, I'm going to listAdd list P2, F2, L2. I'm picking uninteresting names, but I'm picking them in a way so that when I'm testing this, I don't need to remember, is license plate ABC123 Nick or Izad or Carol, right? So I know that if I look for P2, it should be F2 and L2. And so, you know, add some things to your list. And before you do list find, I would do list print. Right? So do some adds and now just call list print with that sentinel node, list print list, and it should print out, you know, P1, F1, L1, P2, F2, L2. So assuming you've got that working and that tells you your add function is working, let's look at list find. Because this is where we're dealing with these funny variables. Okay, so I'm going to do, you know, integer result equals list find. I'll put in the sentinel node, and let's look for plate P1. All right. So here's the start of my call to list find. There's the list, the sentinel node of the list I want to look in. Here's the license plate I want to look for. What I'm hoping is that if this plate is in here, I'll get a 1 back here to tell me it's in there. But I also want to know, hey, what's the first and last name that went with that plate? Well, I can only return one thing here. I'm returning an integer. How am I going to get back the first and last name? So I'm going to pass a pair of variables. And I can just call this, you know, like first and last. And I'm going to declare these as just really big arrays. Right, so I'll declare those first and last to be just arrays of 500 characters. And when I pass those to list find, my hope is that when it comes back from this function call, if result is 1, these two variables now contain, you know, in this case, the strings F1 and L1. So I could do something like, you know, if result equals 1, print first name equals %s, last name equals %s, first last. What I'm doing with this isn't really important. The detail of concern is that when I make this call to list find should do something to change the value of this first and last variable pair. And it changes them to be, you know, the value that was stored in the linked list. So what does our list find function look like, right? So start at sentinel next for each node. And let's suppose, you know, we're calling our node pointer current, the thing that we're using to march through the list. So for each node, see if current plate equals plate. So we've got a linked list. The first node has a plate, first name, last name. Next node has a plate, first name, last name. Move through your list with your usual while loop, right? And at each node, check to see if that node's plate field is the same as the plate you're looking for. Okay, so how do you do this? Use string compare. So see if string compare current arrow plate, comma plate. See if that's equal to 0. Right? We can't use double equals with strings. If you want to know if these are the same strings, pass them as the two arguments to string compare, see if string compare returns a 0. Alright, if this does match, if we found the plate, now we want to copy the information from the node into these variables. And to copy strings, we have to use string copy. So do something like this: string copy first, comma, current arrow, and whatever we're calling it. Let me see what our node structure is. So our node structure, the first name is just called first. So current arrow first, and then string copy last, current arrow last, and then return 1. So the thing that's calling this function just passes two variables, but they're kind of like blank boxes. They're just big arrays that we don't have any particular values in yet. They're boxes into which this function will place the information it finds from the linked list. Does that make sense? Does that make more sense?
Yeah, we'd want to use like fixed size local strings in this case, right? Just like big enough.
Yeah, and in this case, since we know these names are never bigger than 256, just pass, you know, some really big beefy arrays here, because they're just holding spots, right? They're not allocated. If we have 1,000 nodes, we don't have 1,000 of these. It's just a temporary variable. It's figuratively just, you know, a pair of boxes that the function can load values into, so that when we come back to our main program or whatever called this, we can look in those boxes and say, oh, there's the first name, there's the last name.
Yeah, and you know, I got burned pretty bad last night, and I know why in this situation, if you're just trying to invoke list find, it's probably best not to use a mallet.
Mm-hmm.
Because I was finishing up my database reading function yesterday, and I was putting in statically sized strings.
Okay.
Like that. But in that case, it would probably be better to put in mallet strings.
Yeah.
And then make sure you free those when you do a list free.
Mm-hmm.
Because if you were to just invoke list find here with a mallet mallet first and last name,
Mm-hmm.
and you try to free it, I think you would free whatever mallet thing you would have stored in the linked list, right? And then you have like a memory frame.
If you do a string copy, you should be okay. But if you said something like, you know, first equals current arrow first, then you potentially got a problem.
Okay.
Because then if you change first, you change what's actually in that node, and if you free first, then you free that node, and your list is hosed. This is a really subtle aspect of working with pointers. It's one of the reasons I think that, you know, languages moving forward try to get rid of pointers. Like Java, there's no pointers, because it can get you into some tricky issues, including security issues. And it gets into the idea of, like, how do you make a copy of something? And if I have a car star first and I set it equal to this, it will look like I've got a copy of this string. I can print it, I can string length it, and it'll do the same thing as if I had done it on this original thing. But if at some point this thing changes, the thing that I copied will also change. And if I change the thing that I copied, the original thing will change. It's kind of like both things are referring to the actual same locations in memory. And so you don't really have a separate copy of it. You have a separate reference to the same thing. So it's a little like the difference between cloning yourself and just calling yourself two different names. It's a very different effect.
Really kind of makes me appreciate the garbage collected languages.
Yes. Yeah, so things like Java handle all of this stuff for you and allocate stuff as needed and free stuff as needed. So that's what a garbage collector is. It'll go through and get rid of things that are no longer used, things that would be memory leaks. It'll actually locate those and take care of them. And yeah, for all the bad press pointers get, they can be kind of cool to work with, and in most cases, they are what's actually going on at the level of the CPU. When you get down to the machine language level, there's pointers all over the place. There's go-to statements all over the place, right? We try to hide those in higher level languages because humans don't do so well with complexity sometimes. But they're essential elements to making things work at the CPU level, and so if you appreciate that and are comfortable with it, it's nice sometimes to be able to work with pointers and to be able to use go-tos and things like that. So yeah, and there's lots of different reasons we program, so depending on why we're programming today, you know, we may prefer one over the other. All right, so let's, yeah, go ahead.
I think pointers still exist in languages like Java and C#. You just don't have to directly touch them.
Yeah, because you can still throw a null pointer exception in Java, but the language is designed to not really give you direct access to the pointers, but they're being used. Definitely.
The nice thing is, yeah, just throw an exception.
Yeah. All right. So let's look at listAdd. So, you know, list find is doing this stuff, but let's take another look at what the listAdd function has to do. And so the function prototype, listAdd takes a sentinel node and then a plate, first name, last name. And these are all things that you're passing to the function. These should have values in them before you call the function. List find, you need the sentinel and the plate to have a value, but the function itself populates these fields. And that's what's been so different about this function compared to most functions we've written. But listAdd is more traditional. We actually put values into all four of these arguments and pass them to listAdd. And so the behavior of this is a little less quirky. So sentinel node, and then a plate, and a first and a last. And we've done this before, but you know, these things have different levels of meaning depending on where we are in working with something. So I think people are further now, so this may have more meaning this time around. You're going to use your sentinel to move down a linked list when you're searching for something. To add to our list, we don't have to do any searching. We just want to make a new node and put it right in the beginning. Okay, this is your push function from PA2. So that part is not very different. The only thing that's really different is how we create this new node. And so it starts off the way that we're used to, so we can do struct node star new equals malloc. And how many bytes do we need? It depends on what the size of a struct node is. So size of struct node. All right, and then new arrow plate. We really want to set that equal to, you know, the plate that was passed in. But we can't do this. This will give you really, really interesting behavior. If you, yeah, this will be weird. All right. If you do this and you find that, you know, all your nodes in your linked list have the same plate, first name, last name as one node, you may be doing something like this. So
That's what I had last night.
yeah, isn't that fun? www. So this is the effect we want. We want to take the argument plate and copy it into here. But in order to do that, because these are strings, we need to use string copy. So string copy new arrow plate, comma plate.
What if, by the way, when you're, I kind of tackle this a little bit differently, but I think this way is probably a little bit better. When I load in my database for the hash table, I malloc all the variables there and not in listAdd, like you just did there.
Mm-hmm.
But it still does the same. It still has the same effect.
So how much space do you malloc?
I think it just malloc a pointer.
So you did a malloc size of struct. Are you talking about the sentinel nodes in the hash table?
Okay, so So when I load in the database, I read through the database, and I put in, I just malloc like a big enough license plate, as you said, like 257 characters, right?
Mm-hmm.
Like 100 for a first name, 100 for a last name, and then I assign that in the listAdd. But they're malloc not in listAdd.
So where do you malloc them?
I have a function called load database, and as it's reading through the file, it mallocs those variables in the sizes I just told you, and then it assigns it in the listAdd by doing like new arrow plate equals plate.
Okay. So you're passing newly allocated strings to your listAdd function?
Yes.
Interesting. Okay. Yeah, the only reason you're going to lose points for that, though, is because you're only supposed to allocate enough space to hold the actual strings.
Okay.
And what you're doing is effectively the same as just making, static arrays of size 200 or 100 or something like that.
Okay.
So if your license plate is 7 characters, you don't want to allocate 100 bytes for it. And that actually is something I'll be checking for. So this is why you need to allocate space inside the actual listAdd, because that's where you actually know the actual plate that you're going to add. And the way to do that is, and so this was why I left space here, right? If I just string copy into new arrow plate, I'm going to segfault. Because when we create a node, it's got a plate, a first name, a last name, and a next. Each of these is just a pointer. But it's like an integer that we haven't given a value. This is a pointer that we haven't given a value. It's probably pointing to null. And if I try to do this, I will get a segfault. So what you want to do is, before you use, name arrow plate, we want to do a malloc. And how much space do we need to store the plate? Well, it depends on how many characters are in this string. So string length plate. And then you need to add one more for the null terminator. And so now you've got enough space to store your plate plus the null terminator. So do that malloc, and then you can do the string copy. Does that make sense? Did I lose my my microphone?
No.
Okay. Cool. And so you need to do this for the plate and the first name and the last name. And what you're describing is interesting, because technically in your program that's reading the database file, you could still do these more tactical mallocs and then pass those to your listAdd function. But I would suggest, you could do that and it would work, and I would not see anything in the behavior that would cost points. But in terms of abstract data types, right? Your hash function should not need to know that space needs to be allocated inside a node for the plate first name and last name. And if your hashAdd function or your ingest function is allocating space and then passing that allocated space to listAdd, it's kind of breaking that firewall down a little bit. And so I would encourage you to try to adhere to that firewalled behavior where your hash function is doing one thing, your listAdd functions are doing another thing, and so on. And putting your malloc down here in the list code sort of preserves that separation.
Well, most of the hash function should be no more than like 2 to 5 lines, right? Pretty much.
Yeah, and that's the real goal. One of the goals of doing this separation is, once you've got your list code figured out, And you know, you write this code and you write a main program to test it. So you exercise it, make a main program, call listInit, call listAdd, call listPrint, you know, do some finds and so on. Once you have those things working, so that you don't have to go in and monkey with them or look for bugs, and you understand, you know, very clearly that when I call listAdd, these are, you know, empty boxes I'm passing, and when I come back from listAdd, these will suddenly have values in them. So once you've got all that figured out, then your hash functions become really, really trivial, right? Hashadd is really just calling listAdd. There's the plate, there's the first name, there's the last name, but listAdd wants a sentinel node. So how do you figure out what sentinel node you have? Well, you take the plate, you run it through your hash function, and it gives you an index. And you go to your hash table, bracket that index, there's your sentinel node. That's the thing you pass to listAdd along with the plate, first name and last name. And then hash find, exactly the same thing. Say again?
Question for you.
Yeah.
Does that mean that technically we're making a hash table and a list table or a list series?
Yeah, you're making a whole linked list package for these funny types of nodes, and then you're making a hash table package that uses the linked list package. But once you have the lists, the hash table is really just kind of wrappers around the list functions. So how do you write hash find? It's probably, you could do it in one line if you wanted, right? You take the plate, you run it through your hash function that gives you an index. You say hash table bracket index, and that's your sentinel node. And then you call list find with that sentinel node and the plate and the first name and the last name. So it's probably 3 lines if you spell it out in separate steps, but you could actually do it in one line, just a function call to list find. And so this part becomes relatively easy. The new piece of this is the idea of the hash table. But the hash table is really nothing more than a collection of sentinel nodes. And to do your list functions, all you need to know is what's my list? What's the sentinel node? Well, that comes from your hash table. And all of these functions use the plate to figure out which sentinel node in your hash table you want to work with.
So, another question.
Mm-hmm.
Are we using the sentinel node that is the hash table node for our list, or are we using a sentinel node for our list, which we're using in the hash table?
Not the second one. I'm not sure the
Because
first one.
I'm getting a little confused about what kind of sentinel we're supposed to be using, or if we're supposed to be using 2 different kind of sentinel nodes.
So your hash table looks like this. It's an array. And each thing in here is a struct node star. And this struct node star is, you know, a sentinel node to a linked list, and this struct node star is a sentinel node to a linked list, and so on. And so, you know, default case, 100 elements in your hash table. You have 100 linked lists, each with a sentinel node. And part of all of this stuff is choosing which of those 100 linked lists you want to use. But your main program, all it knows about is the hash table. The package of hash functions, your hash.c, right, has this code in here, which will, you know, when you want to add something to your hash table, take the plate, run it through your hash function, and so it's, you know, take your hash function on your plate, and that's the index in your hash table, right? This is a sentinel node. And if I'm trying to add, you know, some information associated with this plate, this would be the first argument to listAdd. That's the sentinel node I pass to the listAdd function, along with, you know, the plate and whatever the first name is and the last name. So this is sort of the main data structure we have, and we use that to find a sentinel node, and then those sentinel nodes get processed by the list functions. I don't know if that answered the question or not.
Sort of.
Okay.
Can I ask a bit of a nitpicking thing about the program?
Sure.
So, in the main program, the first, welcome message is enter a plate or command,
Mm-hmm.
and then every time after that is enter the plate.
Oh, okay.
Can I just have enter a plate or command, every iteration of the loop?
That's perfectly fine.
Okay, cool.
Yeah. So I would say for the hash piece of this, hash init will probably answer most of the questions, because that's where you create this array. And well, let's pseudocode hash init. So hash init takes a hash size, and it should return a hash entry star. All right, so what do we have to do here? Hash table equals. So let's make this an array of hash entry. Malloc hash size times size of hash entry. Alright, find how much space we need for a hash entry. Multiply that by the number of elements in the array, allocate that much space, set hash table equal to it. So I said that these things are struct node stars. That's also what we're calling a hash entry. That's the type def that I suggest in the beginning of this. Right? So make a hash entry struct node star. So each of these things is a hash entry. So for the entire array called hash table, take the length of a single hash entry, multiply by the number of things you want to store, allocate that much space, set hash table equal to that. So our last element is hash size minus 1. Alright, so that creates this table, but there's nothing in the elements of that array. Right? These are all probably null. So we need to make each of these the sentinel node of what will be an initially empty linked list. So for I equals 0 to hash size minus 1, just set element I equal to listInit.
Can you say hash size equal to 1 or minus 1?
Minus 1. And that's just this business, you know, if we have 100 elements, then we go from 0 to 99, because we start from 0. So for, you know, in a C for loop, this would be for I equals 0, I less than hash size, I plus plus, something like that. And so we set element I equal to listInit. Well, what does listInit do? ListInit creates an empty linked list, and it returns the sentinel node's address. And so this assignment statement will say, okay, hash table bracket 0, that's going to be the sentinel node of an empty linked list. The next time through as I is equal to 1, I'll get a new sentinel node for a new linked list. I'll set hash table 1 equal to that. And each time I go through each of these locations in hash table will be a new sentinel node. and it'll be a new Sentinel node to an empty list. And that's really the whole hash-init function. And I think this is the only time you have to call malloc in your hash functions. Is just to make that original array of Sentinel nodes. All the other mallocing gets done in your list functions.
So I got a quick question on the dump command.
Okay.
If you're done with this one.
Yeah, go for it.
So I have my main program passing an arbitrary number, and if you don't put in a cell number, so it's going to be basically set to, I'm just going to say -1. I'll change it to something more obscure later, but I was going to have it set and initialized to like a negative number, and then pass that to the dump function and have the dump function interpret that as they're not specifying, they just dump the whole thing.
Okay.
I'm more concerned though if you put your main program on that it won't do the same thing. Is there some way to code that a little better, or are you going to run it with our main program?
Well, so you could make a separate, hash dump all function that would dump everything, and that could, simply call hash dump for each of the cells from 0 to hashsize -1. And that would not, result in changing the interface. If you were free to
look at, sorry, you still have to look at cell number, right? So
if you made a totally separate function like hash dump all that just took a hash table, and in that function you would call hash dump with, cell num ranging across all the cells, then you could still preserve this interface. This function would work exactly the same, but in your main program, instead of having a loop, you could call hash dump all. And that would be a nice clean way to do it. If you were free to change the prototype, to change the behavior of this, you could just decide, if I pass -1, that's a flag to dump everything. I think that's fine. I don't know if I'm going to use my own main program, but if I do, I'm probably not going to pass it an illegal number to see what it does. Because there's really nothing in here that can respond to that appropriately.
okay.
So yeah, I think that's probably safe. But in general, be cautious with that.
Okay.
Only because.
You're talking about like passing a negative argument.
Yeah, so pass an invalid, so have the main program set whatever your number is. If it wasn't specified, then it sets it to a negative number, and it passes that, and if the function sees the negative number, it knows just to dump all.
And
so
it's.
Like if the user doesn't specify a number of cells, it'll just dump the whole thing that way.
And that's a nice trick. It's a way to sort of combine two functions in one without rewriting this function to dump everything. You sort of utilize the code in here, but you have a flag you can pass that says, hey, I'm not giving you a cell number, I'm asking you to dump all the cells. And that's a convenient thing to do, but be careful, because those things can go out of control pretty easily, especially after 10 years of a program being developed with hooks like that in there. It can start to get cumbersome. But if you use it judiciously, it can be a really nice way to get some behavior you're after. So yeah, I'm okay with that.
Okay.
All right, and question from chat about parsing. So dump 95, right? So to look for the command, star dump, I recommend don't use scanf to try to pull a string out, right? We can use it when we're reading the database because we actually want 3 strings separated by spaces. But for parsing user input, if we're looking for the string dump, you can use something like string compare, right? If you're using fgets command, and remember there's a new line at the end of what fgets ingests and returns, you can just string compare what the user typed in with, you know, star dump \n, and that'll tell you if they typed exactly star dump with nothing else after it. And if they type star dump space, this will not match. If they type star dump 95, this will not match, right? And if you want to know, did they type something like star dump 95? Well, now, you know, we've got an integer in the question. Think about scanf. And search for star dump followed by a %d, maybe followed by, you know, a %s for the extra. And save that as result. And if result is exactly 1, then go ahead and use num as the cell that they want dumped. Right, so if this returns 1, it means that it found a star dump in the beginning, followed by an integer, followed by nothing else. And you know, you can put this pattern in here. I wouldn't recommend doing a %s, a %d, and a %s, and then seeing if that %s equals star dump. That's hard. That's more work than you need to do. But you know, scanf for a star dump followed by an integer, and that will that'll tell you. Let's see, one more time on listAdd. Cool. One more time on listAdd. We are only allocating a string as big as we need to give the arguments to listAdd, right? So there's a few allocates going on. So in our main program, right, or our hash function or whatever is for listAdd, the allocation is happening when you are ready to store into the node. And in that case, yeah, you allocate enough space based on the size of the thing that you're storing. So actually look at the string length of, say, the name, and then add 1 to that to put in space for the null terminator, and then use that to copy your data into. So in listAdd, when you're ready to copy the plate, right, first allocate space based on the number of characters in the plate. Right? Don't make that, you know, 256 or something, because that's way too much space.
I don't know why I didn't do that the first time.
That's okay. I mean, the whole way that you learn programming is by doing stuff, you know, and if you do things, you know, quote, right the first time, you're not going to learn as much. If you do things and you never get tangled up, you're never going to figure out how to get untangled, you know. So I mean, I rarely tried to do things the way that I was supposed to when I was first learning programming. I was always trying to do things differently, and that's part of the learning process. All right, let's see. I don't know if anyone's having issues with command line arguments, but you know, remember, we usually make our main program like that. And we went went through this in a lot of detail in yesterday's lecture, so if you want more detail or a refresher, you can go back and look at the notes from that. But, you know, basically this is the number of things on the command line. And this is an array of strings. So the ways that somebody might try to run your program are plate with a file, plate with a file and a size, plate with a file and some junk that's not a size, plate with, you know, a file and a size and some other stuff.
Oh, do we have to do the case for if they just hit plate?
If they just hit plate, this is an error.
Okay, it is an error. Okay.
Right? If they say, you know, plate and a file and a size and some other stuff, that's an error. If they say plate and a file and they put in another argument but it's not an integer, that's an error. So these are the only two legal cases. Either plate with a database file or plate with a database file followed by a hash table size. And so some of these are pretty easy to discriminate. If they just type plate, argc will be equal to 1. So right in the beginning of your program, one of the first things you can do, check argc. If it's 1, hey, where's my database file name, you know, and exit. If argc is greater than or equal to 4, that's an error. So right after you check to see if argc is 1, check to see if argc is bigger than or equal to 4. If it is, hey, why are you giving me all this stuff? All I want is a database name and maybe an integer. And exit. If argc is equal to 2, you're happy. Make a note, set a variable inside saying, okay, we're going to use a hash table size of 100 because that's the default. And then go on to reading in the input file. These two cases, argc is 3, and now you got to check to see if this thing is an integer or something junky. And so you do your scanf, and the thing you want to scan is whatever this string is. Well, this string will be argv bracket 2. So scan it as a %d, %s, and all the usual business. And if it returns something different than 1, you can say, hey, that's not a valid size, goodbye. Right? If it is, if this does return 1, then this thing is an integer, and whatever variable you put over here for the %d, now that's got the size of the hash table. And so use that instead of 100. And so that's the basic command line setup. But like I say, we did that in a lot more detail yesterday. If you need more detail, or you can go back to 224 and look at your notes from that.
For the error message, do you want us to specify, like, if it is argc, do file needed or something like that, or do you want us to just, because like right now I have it checking for 2 and 3, and then an else statement saying invalid input.
So I think it just says, throw up and exit with a 1. So startup. Your program should report an error if it is not run in one of these two ways. Or, if the hash table size is an integer but it's negative, or 0, right? Just print out an error message and return 1 from your main program.
Okay, so just put like error and then we can add more stuff.
Yeah, you can say, error that's too long, or, whatever you want to do, as long as it's clear that there's an error and we're not going to continue. That's good.
Okay.
All right. Do we want to go over file I/O? Doing fopens and that kind of business?
Make sure you use fclose.
Yeah, make sure you use fclose or you'll get memory leaks.
Yes, please.
Okay. let's mess around with this. So So here's a very simple input-output loop. Nothing to do with files yet. I've got a character array of 200 characters. I'm using fgets to read 200 characters maximum into this array, and I'm reading from standard in, which is, you know, typically the keyboard. And then I'm going to print out the value of this array using a printf, and I'm going to print with a %s. And this is not going to be too startling. So if I run main and I can say this is a test, it tells me my input equals this is a test, and it's got, you know, this new line at the end because that's what fgets does. All right, so that's the usual behavior. And if I want to get rid of that new line, so, you know, fgets puts a new line at the end. If I don't want that there, I can make a modification. So if my input string is testing, and so this is character 0, this is character 1, 2, 3, 4, 5, the G will be character 6. Well, if I'm doing fgets and I type in testing, the string that gets saved will actually be testing followed by a new line. So this new line will be in character 7, and then there'll be a null terminator, which is in position 8. And so when I print the results of fgets, right, we see this extra new line at the end of the word test. I said this is a test, but the string actually contains this is a test followed by a new line, and then we print it out, you know, that closing angle bracket. So sometimes you want to get rid of that new line. And one way to get rid of that is to simply replace that character with, guess what, a null terminator. So if this is my buffer, how do I know that I should replace character 7? Well, use the stringlen function, and stringlen tells you how many characters there are up to but not including the null terminator. So in this case I have 1, 2, 3, 4, 5, 6, 7, 8 characters. So my string length is 8. And in this case what I want to do is set character 7 equal to a null terminator. If my string was hello, that null terminator ends up being in position 5. Well, the string length will be 1, 2, 3, 4, 5, 6, HELLO new line. So there's a pattern. If my string length is 8, I want to wipe out character 7. If my string length is 6, I want to wipe out character 5. And this is just another way of looking at the notion that if you have an array of n characters, the last character is at index n minus 1. So if I do buffer bracket string length of buffer minus 1, that's the index of the last character, which is a new line. If I set that equal to a null terminator, that should strip off the new line. It basically replaces this thing with a \0. So this is useful to do sometimes. Right, make that replacement, and I'll need to include string. And so now if I do this, and I say this is a test, it tells me my input is this is a test, and there's no extra new line at the end. And so yes, as someone said in chat, now we've got 2 null terminators on here, but that's okay. With all of our strings, once we encounter a null terminator, everything after that is completely ignored. And so that won't do any harm. Alright, so this is reading from standard in. What if we want to read from a file? So let's make a file. And so we need a file of type file star, uppercase file. We need a variable of type file star. And this is a variable that's going to come from fopen, and it's going to be sent to fgets. So let's give this a value, fp equals fopen, and if you look at the manual page for fopen, it takes an array of characters, that's a string, which is the name of the file you want to open, and it also takes a string which is called the mode. And the mode we want in this case is R, open the file for reading. And since you don't have write access to the file, if you open it, for example, for R+, which is for reading and writing, I think you'll get an error. So to fopen, we're going to open the name of the file, followed by an R, and these have to be in double quotes because they're strings. And that says open the file for reading. And then in fgets, instead of reading from standard in, we're just going to read from fp. So if I run this, I'm going to segfault. And the reason I'm segfaulting is because this file does not exist. I don't have a data.txt. And if you look at the manual page for fopen, and you go down to where it says return, upon successful completion it returns a file pointer, otherwise null is returned. So if it can't open the file, it will return the value null, and so I can check for that. So did we open a file? So as soon as I call fopen, before I try to use fp to get a line, I'll check to see if it's null. And if it is, I'll just print an error message and say, hey, I can't open that file. And so now if I run main, it says cannot open file. So if I make a data.txt, and I throw some stuff in it, and I run main, it reads the first line of the file. And if I do this 3 times, it reads the first 3 lines of the file. And if I do this 5 times, right, so 5 times I'm doing an fgets, removing the new line and printing it out. Well, you know, it reads the first 3 lines of the file, but the next time it reads, you know, most of that line, and the next time it reads a little less of that line. It's doing some weird stuff here, right? But clearly, you know, after I've read this 3rd line, I've hit the end of the file. My data.txt only had 3 lines in it, and so I shouldn't keep trying to read from it. And so I need to be able to detect that I've hit the end of the file. And so let's read until we hit the end of the file. And if you look at the manual page for fgets, remember fgets returns null when it hits the end of the file. And so we can say, well, null is not equal to fgets. So if this returns something different than null, we know that buffer is the next line of input. And so let's go ahead and trim that off and print it. and then let's exit our while loop. And so if I run this, it read exactly 3 lines from my file, and then it exited. All right, and so a little detail here, we want to call fclose when we're done with a file. So after I'm done using fp, let's close fp. And if you don't do that, Valgrind will report a memory leak, I believe. Because as long as the file's open, there's resources that are being used. So I can do that.
Speaking of that, I had sent you that email about Valgrind messing with my arguments.
Yeah.
I don't know what happened the first time I tried it, because I sent you the message, and then after you messaged me back, I checked it again, and it worked fine.
Oh, interesting.
What was going on.
Okay.
With the program, maybe.
Weird.
Yeah.
So this is a pretty fundamental input loop, right? That reads, you know, 1 line at a time into here. We're cleaning up the new line at the end, and then we can do whatever we want with it, right? So if I get rid of this, right? This is just basically giving me a copy of my file. And if I want to make this a little more useful, I could process my command line arguments. And so instead of fopening data.txt, I could open argv bracket 1. Because remember, when I run a command, you know, this is the name of my command. If I put an argument after it, well, this is argv bracket 0. This will be argv bracket 1. And so if I want to read the name of the file I want to process from the command line, I can just open it as argv bracket 1. And I can improve my error message. And if you can't open it, I'll put in an error message saying can't open file, and I'll put the name of the file there. So if I say main data.txt, it shows me the contents of my text file. If I say main.c, it shows me the contents of my main.c file. If I say main cat walking on keyboard, it says cannot open file cat walking on keyboard. And wonderfully, if I just say main, I get this weird error message. Sometimes this will segfault, but on this system it's going to say cannot open file null, and that's a little weird because I didn't ask it to open a file null. So this is where we would use argc, right? Before we use argv bracket 1, did the user give me a file name? If they didn't give me exactly, sorry, this should be 2. If they didn't give me exactly 2 things on the command line, I'll print a message saying, please say main file name. And I'll just give up on them at that point. So now if I say main, please say main file name. If I say main and I put a bunch of things, please say main file name. If I say main file name, it says cannot open. If I say main and the name of a file, it prints out the contents of the file. So that's a bunch of examples around command line argument handling and opening a file, reading from a file, processing the file, dealing with new lines at the end, closing the file, and so on and so forth. So I'll toss this code onto the shared server in a separate area right after class. But that's some stuff that might help you with some of the technical details of PA3. All right, so we are pretty much out of time, so let me leave it there. Thursday we will continue talking about binary trees. So we'll keep digging into this recursive algorithm business, and I want to look at details of how nodes are ordered in a binary tree to make what's called a binary search tree, and we'll keep looking at recursive algorithms, and we'll start actually writing some code and sketching out some detailed algorithms for searching a tree, inserting into a tree, and printing a tree. And this will get us into kind of the heart of what we'll need to be doing for PA4 eventually. All right, have a great afternoon, and I will see everybody next time. Thank you.
Thank you. See you later. Thanks. Have a good day.
Thanks, you too.